Welcome to the third video on stoichiometry and the more concept. So far I've looked at introduction to the more. We also looked at calculations that are derived or that involve equations. In this video, we're going to take a look at gas volumes. Then from there, in the next video, we're going to look at other calculations that have to do with stoichiometry and the more concept. Let's start it. So on gas volumes, we're going to start with what is called Avogadros Law. So Avogadros Law states that the volume of a gas is directly proportional to the number of moles of the gas molecules present if the pressure and temperature are constant. What this basically means is if you increase the volume, the number of moles should increase. If you increase the number of moles of the gas, the volume should increase. So mathematically, it can be expressed as number of moles equals volume of gas over molar volume. So volume of gas is just the volume of the gas, then molar volume, it's a constant. So there's something that I'm going to show you which you should concentrate on and you should keep it at heart, and that is the value of molar volume. So this can also be written as, of course, using symbols N, which is number of moles, is equal to V, which is volume of the gas, and Vm, which is molar volume. And sometimes we like to solve in form of this. In short, if you make this V subject, you're going to have this. So usually we are given number of moles and we need to know the volume of a gas when we know the number of moles of that gas present. Sometimes, of course, we can know the volume, then we can determine the moles using this formula. So it's the same formula, I've just made V subject here. So N is number of moles, of course the units are mole. Volume is centimeter cubed or decimeter cubed. So you'll be using two units for volume, centimeter cubed or decimeter cubed. And Vm, which is molar volume, is just centimeter cubed per mole or decimeter cubed per mole. So what I said as something you should keep by heart is this golden knowledge I'm sharing. So there are two conditions where we do our measurements. The first one is called RTP, which is room temperature and pressure. So at room temperature and pressure, the volume of 1 mole of any gas is 24 decimeter cubed or 24,000 centimeter cubed. So always when you have been given a calculation and they have stated that the volume is, or the calculation or the reaction is happening at RTP, just know that the volume of that gas, I mean the molar volume of that gas is 24 decimeter cubed or 24,000 centimeter cubed. So this is what is called molar volume because it's the volume of 1 mole of any gas. That's what molar volume is. Then at STP, which is standard temperature and pressure, the volume of 1 mole of any gas, in short, the molar volume is 22.4 decimeter cubed or 22,400 centimeter cubed. So these are the two figures you have to keep at, but don't worry, they are during an exam they are attached, they are there on the periodic table. Just on the bottom of the periodic table you're going to find these values which you can use in your calculations. So let's take a look at an example. Calculate the number of moles of carbon dioxide molecules present in 24 centimeter cubed of the gas at RP. So they want us to determine the number of moles of carbon dioxide if its volume is 24 centimeter cubed. So this is very simple. We just use proportionality here. We're going to say, actually I'll just use our formula. Number of moles is equal to volume over molar volume. We're looking for number of moles. The volume we have been given. What is needed is the molar volume, which we know. So it is at RTP, so we know the molar volume at RTP. So at RTP, molar volume is 24 decimeter cubed or 24,000 centimeter cubed. Now this volume we have been given is in centimeter cubed, so we're going to use the value that has centimeter cubed instead of decimeter cubed, because the volume that has been given is 24 centimeter cubed. I mean is in centimeter cubed, so I want to work with centimeter cubed. So ensure that your units are uniform. So we're going to put the volume we've been given divided by the molar volume, and we're going to get 0.01 moles of carbon dioxide. The second question is, what is the volume of the following gases at STP? So here we are going to start to calculate the volume of gases at STP. So the first one is 2.8 times 10 to the power negative 3 moles of nitrogen N2. So this is the number of moles, so we need to find out what volume this is at STP. The second one is 3.2 grams of oxygen. So here they haven't given us moles, they have given us mass, meaning that this mass has to be converted to moles, then we convert the mole to the number of volume, because we can tell the number, to volume, because we can tell the volume from the number of moles of a gas present. So start with A. So we're going to use the version of the formula where V is the subject, where we say volume is equal to number of moles times molar volume. So number of moles for nitrogen we have been given is 2.8 times 10 to the power negative 3. So we multiply this by the molar volume at STP, and at STP. So concerning the units, I'm going to use centimeter cubed or decimeter cubed. Here it's all up to you. So 2.8 times 10 to the power negative 3 mole times 22.4 decimeter cubed per mole. I've decided to use decimeter cubed because this one is easy. Like the numbers are not as, the digits are not as many as when we're using centimeter cubed. So when there's a choice, I prefer using decimeter cubed. So if you multiply these two, you're going to get 0.0627 decimeter cubed as the volume of 2.8 times 10 to the power negative 3 moles of nitrogen. We go to B. So for B again, first, like I said, we have to get the amount of moles present in that mass. So we use the formula that we had discussed when we were talking about introduction to mole. So N is equal to mass over molar mass. So 3.2 grams is the mass of being given. Molar mass of nitrogen is 32 grams per mole. I'm sure you know how to calculate that. So when you divide, you're going to get 0.1 moles of our gas. So the next job is now to convert this to the volume. So we use this same formula, 0.1 more times. Again, we use decimeter cubed. If you want, you can use centimeter cubed. There is no any issue there. So when you multiply, you're going to get 2.24 decimeter cubed as the volume of the gas present. Now, with this understanding, can we deal with equations where actual reactions are happening? So the concept is the same, just like the way we were working with equations. Even here it's going to hold. The only new knowledge that has come is the relationship between moles and volume of gases. So here's a question. What volume of hydrogen measured at STP is produced when 0.35 grams of lithium reacts with water? So there is a reaction of hydrogen and lithium, which is here. So lithium reacts with water to form lithium hydroxide, which is the base, plus hydrogen. So always make sure that the equation you're working with is balanced. So for this one, it was usually when you're given an equation, it should be balanced, but there are certain situations where it cannot be balanced, so you end up getting wrong figures. So if you look at this one, there are 2 moles of lithium here. Even here there are 2. Hydrogen, we have 4 hydrogen atoms. Here we have 2, and here we have 2. For oxygen we have 2, and here we have 2. So this one is balanced. With that being said, what do they want? First, we are working at STP. Okay, so we should have that figure for STP in mind. Then they have given us the mass of lithium. What they want is the volume of hydrogen. Okay, so they have given us the mass of lithium, they want the volume of hydrogen. We know that we can get volume from number of moles of hydrogen that are going to be produced. So for now, let's think about mass and moles. So go back to mole mass kind of calculations. Another way in which you can easily deal with this is this mass, you convert it to number of moles. So once you know the number of moles that are present in 0.35 grams, you're going to use the coefficients. That is, 2 moles of lithium produces 1 mole of hydrogen. What about this number of moles? How many moles of hydrogen are they going to produce? When you do that, the amount of moles of hydrogen you're going to get, you convert to volume. So first we get the number of moles of lithium, mass over molar mass, so 0.35 grams over 7 grams per mole, which gives us 0.05 moles of lithium. Next, we use the coefficients. So 2 moles of lithium produces 1 mole of hydrogen. Okay, so this is a reaction. Always 2 moles of lithium will be producing 1 mole of hydrogen. But in our actual experiment, we have 0.05 moles of lithium. So how many moles of hydrogen are going to be produced if we only have 0.05 moles of hydrogen, of lithium? So we can use the coefficients. 2 moles of lithium produces 1 mole of hydrogen. What about 0.05 moles of lithium? How many moles of hydrogen are they going to produce? So we can do cross multiply here. 2 moles of lithium multiplied by x, 0.05 moles of lithium multiplied by 1. We're going to get wait, I won't show you how this is done because this proportionality. You do 2 times x, you have 2x. 0.05 times 1, you have 0.05. You divide both sides by 2, so you're going to end up with 0.025 moles of hydrogen. So these are the number of moles of hydrogen that are going to be produced. Now that we know the number of moles, let's convert to volume. So with this figure, we know that volume is equal to number of moles times molar volume. So we can just plug in number of moles is 0.025 moles times molar volume at STP is always 22.4 dm cubed per mole, which gives us 0.56 dm cubed as the volume of hydrogen to be produced at STP. The second question, what mass of ammonium sulfate is required to produce 5.6 decimeter cubed of ammonia at STP by the reaction shown below? So our sodium hydroxide reacting with ammonium sulfate to produce sodium sulfate and water and ammonia. So they are saying what mass of ammonium sulfate is required. So what mass of this is required to produce 5.6 decimeter cubed of ammonia. 5.6 decimeter cubed of ammonia. So we're talking about this gas here. Okay, so what we're learning only applies to gases. The idea of converting moles to gas and gas to moles, moles to volume and volume to moles, is only for gases. So we have 5.6 decimeter cubed of ammonia to be produced. So we want the mass of ammonium sulfate that is going to give us 5.6 decimeter cubed of ammonia. So we're going to take advantage of more ratios. I'm talking about the coefficients. So let's solve this. So first, this gas have been given, the volume have been given. Let's see how many moles is present in the volume have been given. We know on paper the reaction is like this, but this volume, how many moles are in this? Once we know the amount of moles that are in this volume, we are going to use the mole ratios here from the reaction. Then we see how many moles of ammonia can produce the moles of how many moles of ammonium sulfate are needed to produce the moles we're going to get of ammonia. So we are going to say number of moles of ammonia is equal to volume of ammonia over molar volume. So we are working at STP, which means 22.4, and this 5.6 which we have been given. When we divide, we get 0.25 moles of ammonia gas produced. So we're going to now take advantage of the mole ratios. So we know that 1 mole of ammonium sulfate produces 2 moles of ammonia. So how many moles of ammonium sulfate are going to produce 0.25 moles of ammonia? When you do cross multiplying and dividing, you're going to get 0.125 moles of ammonium sulfate. Now that you have this amount of moles of ammonium sulfate, next is to get the mass. So we use the thing we learned at first, which is mass is equal to number of moles times molar mass. So this is not different from what we did in the previous example, just that I have solved for m. Otherwise, it's supposed to be number of moles is equal to mass over molar mass. So when you solve for m, which is mass, you're going to have this. With that being said, we can plug in now. So when you plug in molar mass for ammonium sulfate, you have to calculate. That is nitrogen, 4 hydrogen, nitrogen by 2, hydrogens by 8, 4 times 2, sulfate, oxygen by 4. So when you do that, you're going to get 132 grams per mole as the molar mass of ammonium sulfate. Then when you multiply, the mass you're going to get is 16.5 grams of ammonium sulfate. Next, we go to volume ratios. So there is another way in which Avogadros Law can be stated, and the other way is equal number of volumes of gases at the same temperature and pressure contain the same number of moles. So if you have two different gases, let's say hydrogen and nitrogen, so hydrogen is 20 centimeter cubed and nitrogen is also 20 centimeter cubed. It means the number of moles present in these gases are the same. In short, let's say we've got this reaction, hydrogen reacting with chlorine, which produces hydrochloric acid. So here, hydrogen, we have 1 mole, chlorine 1 mole, and hydrochloric acid 2 moles. So what this means is the amount of volume we have for hydrogen, we are going to call it 1 volume, it should be equal to chlorine, which is 1 volume, and for hydrochloric acid, it should be 2 times. So in short, let's say we have 1 centimeter cubed for hydrogen. It means even for chlorine, we should have 1 centimeter cubed, and hydrochloric acid, we should have 2 centimeter cubed. So the mole ratios are proportional to the volumes of the gases. So there is this example. So I've got this equation. We have CH4, 2 oxygens, carbon dioxide, and water. So what volume of oxygen is needed to react with 40 centimeter of methane? Methane is this one, CH4. So what volume of oxygen is needed to react with this? So this is very simple. Let's see question 2. What volume of carbon dioxide would be produced? What volume of carbon dioxide is going to be produced in this reaction? So let's solve the question A. So question A, we know 1 volume of methane produces or needs 2 volumes of oxygen in this reaction. 1 volume of methane needs 2 volumes of oxygen. But the question is, what volume of oxygen is needed to react with 40 centimeters of methane? So we have 40 centimeters of methane, but we don't know the equivalent of 40 centimeters of methane to oxygen. So we do cross multiply again. So 1 times x and 40 times 2 is going to give us 80. So we need 80 centimeter cubed of oxygen. Simple. B, what volume of carbon dioxide would be produced? So we won't even solve here, let's just analyze. So what volume of oxygen is needed to react with 40 centimeters of methane? So 40 centimeters of methane, in this equation, we have 1 mole of methane producing 1 mole of carbon dioxide, meaning whatever volume of methane is going to produce an equivalent volume of carbon dioxide, meaning 40 centimeters of methane is going to produce 40 centimeters, 40 centimeter cubed of methane is going to produce 40 centimeter cubed of carbon dioxide. But if you want, of course, you can solve, but you can tell here it's so direct. Finally, we'll take a look at relative molecular mass of gases. So sometimes you can be given the density of a gas and maybe the volume, and they can ask you to get the relative molecular mass of a known gas. So they won't tell you what that gas is, because if they tell you, you can just use the periodic table to get the relative molecular mass, but they won't tell you what the gas is, so that you use another method to calculate relative molecular mass. But for all my science students, and for all those of course who are doing science, this is simple. How so? Because the formula is so familiar. It's this: density is equal to mass over volume. So this is what you're going to use. You just get density and your volume, which if you solve for mass is density times volume. So density multiplied by volume, that's all. So here's an example. The density of a gas is 0.71 grams per decimeter cubed at RTP. What is the mass of the gas? What is the mass of the gas? So of course you can end up asking yourself, but where is the volume? So we are going to use the molar volume. So mass is equal to density times volume. Mass is equal to 0.71 gram per decimeter cubed times 24 decimeter cubed. So the mass of the gas is 17.04 grams. So this is okay to use the molar volume, because the molar volume is the volume of 1 mole of a gas. And since we're just calculating relative molecular mass, which is about 1 mole of a substance. Hope you get the thinking there.